Hello, everybody. In the previous lecture, we have derived two very important formulas that relate the concentrations of electrons and holes to the effective densities of states in the conduction and the valence band, and the probabilities for a particular state to be either occupied for electrons or empty for holes. Those two formulas involved one unknown parameter, the Fermi energy. Without knowing the Fermi energy, these formulas are pretty useless. So for general semiconductors, we would have to make an extra effort to figure out the Fermi energy or to figure out the way around it. There is one type of semiconductors where you can figure out the electron and hole concentrations without knowing the Fermi energy. These are the intrinsic semiconductors, and they have the property that electrons and holes have the same concentration in intrinsic semiconductors. So in this lecture, I will tell you about intrinsic semiconductors, how to find the electron and hole concentrations in intrinsic semiconductors, and how to find the Fermi energy in intrinsic semiconductors. Then I will move on to the more general semiconductor type, the so-called extrinsic or doped semiconductors, in which you introduce deliberately shallow impurities, that is, impurities which are easily ionizable. They easily turn into positive or negative ions. And as they do, they either give an electron to the lattice or take away an electron from the valence band from the lattice, thereby creating extra electrons or extra holes. This possibility to control the charge and the concentration of the charge carriers in semiconductors is what makes semiconductors so technologically important. After talking about the extrinsic semiconductors and the charge carrier concentrations in those, I will introduce finally a very important visual tool to analyze semiconductors qualitatively and quantitatively. This tool is based on drawing the energy band diagrams. So let's begin with the intrinsic semiconductors. Intrinsic semiconductors are pure semiconductors, that is, no impurities whatsoever. Each electron in the conduction band was originally in the valence band in intrinsic semiconductors. It got promoted from the valence band into the conduction band by thermal activation. And when an electron goes from the valence band to the conduction band, it leaves one hole behind. So for each electron in the conduction band, there is one hole in the valence band. And for this reason, the carrier concentrations for electrons and for holes are the same, and naught equals P naught. N for negative electrons, P for positive holes. The subscript 0 signals thermal equilibrium. Since both types of charge carriers have the same concentration, there is a special symbol used for electron hole concentration in intrinsic semiconductors. It is N sub I. N stands for concentration. Here, I stands for intrinsic. Now, how do we find the intrinsic carrier concentration? We start with the general expressions for the electrons and holes that we have derived in the previous lecture. So for electrons, it is the effective density of states, and see near the bottom of the conduction band. That is the number of states per unit volume that may or may not be occupied by an electron. If you multiply this effective density of states with the probability for a particular state to be occupied by an electron, here is this probability given by the Boltzmann factor, then you will get the concentration of occupied states in the conduction band. That is, you will get the concentration of conduction electrons. For holes, similar formula, but instead of the conduction band effective density of states, you use the valence band counterpart. And instead of the probability for a state to be occupied, you use the probability for a state to be empty. That is no electron in this state. In other words, the state is occupied by a hole. A hole is like not having an electron in a particular state, means having it filled with a hole. Notice that the Fermi, yes, and both formulas involve Fermi energy, which is unknown. But notice that in the first formula, electron formula, the Fermi energy enters with the plus sign in the exponential. Minus times minus gives me a plus. And in the second formula for the holes, Fermi energy enters with the minus sign. So if we multiply them together, then the Fermi energies will mutually cancel, like that. The product NC and V is the same in intrinsic semiconductors as the square of the intrinsic concentration. The product N naught P naught is intrinsic concentration squared. It equals the product NC and V, the product of the effective densities of states, times exponential to the power minus the energy at the bottom of the conduction band minus the energy at the top of the valence band. This energy difference, EC minus EV, is the band gap, divided by the thermal energy KT. So taking the square root of this expression for intrinsic concentration squared, we get the intrinsic concentration as the geometric average of the effective densities of states in the two bands, and C and V square rooted, times exponential to the power negative band gap energy divided by twice the thermal energy 2kT. I would like to make two comments about this formula. Comment number one, this formula is very sensitive to both the size of the band gap and the thermal energy KT. And the reason is that exponential is such a strong function. It is stronger than any polynomial function. If you compare two functions, e to the power x and x to the power, let's say, 1,000,000 or 1,000,000,000, whatever, then eventually exponential will win. Exponential function will give you larger values than x to any power that you want. So yeah, so if you increase the argument of an exponential by a factor by 2.3, so you add 2.3 to the argument, the value of the exponential gets increased by a factor e to the power 2.3 by 10 times. The second comment that I wanted to make is about this product, N naught P naught is N intrinsic squared. So notice that the product N naught P naught has the same value, N intrinsic squared, no matter where your Fermi energy is. Now, it is possible, as I already said, it is possible to control the concentration of electrons and holes by introducing those impurities, by doping the semiconductor. And when you dope the semiconductor, you will shift the Fermi energy either up or down, closer to the conduction band or to the valence band. No matter how you dope the semiconductor, the product N naught P naught will be equal to the square of the intrinsic concentration, no matter what. Actually, there are three comments that I wanted to make. So here is comment number three. Comment number three. So this statement N naught P naught is N intrinsic squared is called the mass action law, or the law of mass action. That was not the comment. The comment is this. It is not universally valid. It is valid as long as the expressions, these expressions for the electron and hole concentrations are correct. These expressions have been obtained using Boltzmann's approximation. Boltzmann's approximation allows you to replace the Fermi-Dirac distribution with the exponential function, with an exponential function, And this replacement is possible as long as the Fermi energy is sufficiently far away from the bent edges. So it again, because exponential to the power 2.3 is 10, you want, and in the Fermi-Dirac distribution, you have 1 divided by 1 plus exponential to the power energy minus Fermi energy over kT. So as long as the Fermi energy is below the conduction band edge by at least 2.3 thermal energies and above the valence band edge by at least 2.3 thermal energies, you can use Boltzmann's approximation. And this is the validity range of the mass action law. Fermi energy must be separated from the band edges by at least 2.3 times the thermal energy. Now, 2.3 times kT is not a big number. Typically, the band gap has the value, let's say, 1 electron volt, the typical band gap value. Thermal energy at room temperature is 26 milli-electron volts, so 0.026 milli-electron volts. So 2.3 times the thermal energy will give you something like 60 milli-electron volts, 0.06. So yeah, which is much smaller than the band gap energy. When the Fermi energy gets too close to either band edge or gets into a particular band, valence band or the conduction band, the semiconductor in that situation is called degenerate semiconductor, and it behaves more like a metal than a semiconductor. It acquires metal-like properties. And this happens if your doping is very high. If your doping is comparable to the effective density of states in either band, doping concentration. All right, now, so this is the main formula from this slide. And intrinsic is geometric average of the effective densities of states in the conduction and the valence band multiplied with exponential to the power negative band gap energy divided by twice the thermal energy. Next, I would like to tell you how to use this formula in the most efficient way. The thing is that it is sufficient to measure the intrinsic concentration at one particular temperature, let's call it the reference temperature, and usually in semiconductor physics, the standard reference temperature is 300 kelvins. So once you know the intrinsic concentration at the reference temperature T0, you can find the intrinsic concentration at any other temperature. In order to see how this is done, notice that the intrinsic concentration is a product of two terms. The first term is the geometric average of the effective densities of states and C and B square rooted. The effective density of states depends on temperature as temperature to the power 3/2. The product in C and B is proportional to temperature cubed. The square root of this product is proportional again to the temperature to the power 3/2. And then you have this exponential factor, e to the power negative band gap energy divided by 2 kT. So if you know the geometric average of the effective densities of states at a particular temperature T0, you can recalculate this geometric average to any target temperature T. Likewise, the exponential. If you know the exponential at a particular reference temperature T0, you can recalculate the exponential at any desired target temperature T. So here is the formula, how you do it. This term, so N intrinsic at a desired temperature T is intrinsic concentration at the reference temperature T0, usually taken to be equal 300 kelvins, times the ratio T over T0 to the power 3/2 times this exponential. Now, the ratio T over T0 to the power 3/2 recalculates the geometric average of the effective densities of states in C and P, because this geometric average behaves with temperature as T to the power 3/2. So at temperature T0, it is something times T0 to the power 3/2. At the temperature T, it is something times T to the power 3/2. So you need to multiply by T over T0 to the power 3/2 to recalculate from T0 to T. Then we have exponential, and this is how you recalculate the exponential term in the intrinsic concentration. You need to multiply with exponential. So see here in the original formula, you have minus band gap over twice the thermal energy. So multiply with band gap divided by twice thermal energy at the temperature T0. And then multiply again by exponential to the negative band gap over twice thermal energy at the temperature T. Now notice that the band gap, the temperature enters as an argument in the band gap. The thing is that band gap in semiconductors does slightly depend on temperature. The primary reason for the temperature dependence of the band gap is thermal expansion. As the material gets warmer, it expands, the lattice constant gets bigger, the overlap of the wave functions that belong to neighboring atoms gets smaller, the amplitude of the effective periodic potential in which each electron finds itself gets smaller, the band gap gets smaller. There are several empirical formulas for the temperature-dependent band gap in semiconductors, and one of the most popular ones was proposed by a Canadian physicist, Yatendra Varshni. I hope I pronounce it correctly. Not sure which syllables need to be stressed. So I assume the first ones, Yatendra Varshni. So this formula was invented 60 years ago. And here it is. The band gap at the temperature T. Now, as per usual, in semiconductor physics, temperature is measured in kelvins. Band gap or energies are measured in electron volts. Recall that 1 electron volt is the energy acquired or lost by an elementary charge, 1.602 10 to the negative 19 coulombs, as it goes through a potential difference of 1 volt. So the band gap at the temperature T is band gap at absolute zero temperature minus this temperature-dependent function, alpha t squared, divided by t plus beta, where alpha and beta are parameters and t is the temperature measured in kelvins. So here are the parameter values for silicon. We see that at absolute zero temperature, the band gap is 1.17 electron volts. And if you plug in all the numbers, you will find that at room temperature, 300 kelvins, the band gap is smaller, and it has the value of 1.12 electron volts. So increasing the temperature by as much as 300 kelvins, the band gap changes by something like 4%, less than 5%. Once you know how the band gap depends on temperature for your semiconductor, and you know the intrinsic concentration at 300 kelvins, then you can figure out the intrinsic concentration at any other temperature using this formula. Notice that in silicon, the intrinsic concentration at the room temperature, 300 kelvins, has a nice and pleasant value of 10 to the 10th inverse cubic centimeters. Easy to remember. All right. In some problems, it is desirable to know the Fermi energy. And for intrinsic semiconductors, once we know the electron and hole concentrations in an intrinsic semiconductor, it is easy to figure out the Fermi energy in intrinsic semiconductors. In intrinsic semiconductors, the Fermi energy is denoted as EFI, I for intrinsic. So let us return to the expressions for the electron and hole concentrations, which in intrinsic semiconductors are the same. And now let's take the ratio of the electron to hole concentration, which the value of this ratio is 1. On the other hand, this ratio is the ratio of the effective densities of states, Nc over Nv, times exponential to the power, okay, negative Ec minus E Fermi, minus Ev minus E Fermi. So negative Ec plus E Fermi minus 2E, e to the negative Ec plus Ev minus 2E Fermi intrinsic divided by kT. So just divide one concentration by the other. And then use this identity that this ratio is 1 to solve for the intrinsic Fermi energy. So what do you get? You get Ec plus Ev over 2. Now the energy, this energy, arithmetic average between the conduction and valence band edge energies, is the energy exactly in the middle of the band gap. Then you have the temperature dependent term, which is half the thermal energy times the natural logarithm of the ratio of the effective densities of states in the valence and in the conduction band. Now, the effective density of states depend on the effective mass and the thermal energy, as it is proportional to the product of the effective mass and thermal energy to the power 3/2, with the same proportionality constant for the conduction band and for the valence band. So the ratio Nv over Nc is just the ratio of the effective masses, whole effective mass to electron effective mass, to the power 3/2. Okay. Natural logarithm of a number raised to the power 3/2 is 3/2 times natural logarithm of that number. So kT over 2 gets multiplied by 3/2. This gives me 3/4 kT, natural logarithm of the ratio of the effective masses. Whole effective mass to electron effective mass. So at absolute zero temperature, the intrinsic Fermi energy happens to be exactly in the middle of the band gap. Recall our discussion of statistical physics, where in one of the lectures I told you how to calculate the location of the Fermi energy, and we came up with a similar formula. It's absolute zero temperature. At absolute zero temperature, it is the energy in the highest occupied plus lowest unoccupied energy level divided by 2. Or quantum state, highest occupied plus lowest unoccupied quantum state divided by 2. Here, the highest occupied state is at the top of the valence band. Lowest unoccupied quantum state is at the bottom of the conduction band divided by 2. So that's the Fermi energy at absolute zero temperature. Then as you increase the temperature, the Fermi energy starts to shift slightly, very slightly. Because, well, first, thermal energy, even at room temperature, thermal energy is not very big. It is 26 milli electron volts. So if the band gap has the value of 1 electron volt, then Ec plus Ev over 2, the first term, is half an electron volt, or 0.5 electron volts away from either of the two band edges. So half an electron volt here, and something of the order of 26 milli electron volt here. Now, actually, it's actually smaller than 26 milli electron volts, because typically the electrons and holes have similar effective masses. So natural logarithm is taken of a number which is close to 1. Natural logarithm of 1 is, of course, 0. So now, but in general, this correction is not exactly 0. So the Fermi energy is close to, but not exactly in the middle of the band gap. And as the temperature increases, this temperature correction term shifts toward that band which has the smaller effective mass. Okay? So if holes are heavier than electrons, then the ratio is bigger than 1, m hole to m electron effective is bigger than 1. Natural logarithm of a number which is bigger than 1 is positive. And as you increase the temperature, the second term increases. So the Fermi energy shifts up toward the conduction band. And likewise, if the electrons are heavier than holes, then the natural logarithm is taken from a number which is smaller than 1, but of course bigger than 0. And so the Fermi energy in the respective intrinsic semiconductor will shift down toward the valence band. Good. So now that we have understood a little bit we have understood intrinsic semiconductors. Now let's talk about extrinsic or doped semiconductors. As I said earlier, you can control the sign and the concentration of your charge carriers by deliberately introducing impurity atoms. Let's say your semiconductor is silicon. Silicon has valence 4, that is, silicon atoms. Each silicon atom forms covalent bonds with 4 nearest neighbors, forming this tetrahedron, which are located at the corners of a tetrahedron. And each silicon atom uses its 4 valence electrons to form those bonds. Now let's say you replace some of those silicon atoms with atoms from the fifth group 5 elements, for example, with phosphorus or with arsenic. Okay, so let's say with arsenic or with, okay, as in this diagram. Group 5 elements have 5 valence electrons, only 4 of which are needed to form chemical bonds with silicon atoms. What does the 5th electron do? Well, the 5th electron becomes loosely bound to its host atom, let's say phosphorus atom or silicon atom. The binding energy is not smaller than the thermal energy, but slightly bigger typically, but not by a lot. So thermal activation is sufficient to easily ionize that impurity atom, and so the impurity atom turns into a positive ion, sitting tightly in the crystal lattice. And the electron that it gave away to the lattice goes into the conduction band. Why does it not go to the valence band? The answer is because there are many states in the conduction band which are empty. And there are only a small number of the states in the valence band which are empty. So, and Pauli exclusion principle, due to the Pauli exclusion principle, that electron from the impurity phosphorus or arsenic atom, whatever, goes into the conduction band, because conduction band has much more states where that extra electron can go to. So such atoms are called donors because they give electrons. Donner in français, in French, donner means to give, right? They give electrons. This type of doping is called donor doping. The semiconductor, which is doped with donors, is called the N-type semiconductor, N for negative. Its majority and electrons become majority charge carriers. So if due to donor doping you increase the concentration of electrons by, let's say, 1,000,000 times, then the concentration of holes will decrease by 1,000,000 times. Why by 1,000,000? Because of the mass action law that we have already discussed right here. If you increase N0 by a given number of times, then P naught will have to decrease by the same number of times so that the product N naught P naught remains the same, N intrinsic squared. All right, now let's say you are doping the semiconductor with a different type of impurities. Your semiconductor is, let's say, again, silicon, group 4, and you are doping the silicon with a group 3 element, such as boron or gallium or something else from group 3. Group 3 element has valence 3, but it needs 4 electrons to form chemical bonds with the neighboring silicon atoms. So what does it do? It takes a valence electron, that is an electron from the valence band, from one of the neighbors to form own chemical bond. In this way, the impurity atom, boron, like boron in this case, turns into a negative atom, negative ion, and the crystal lattice gets an extra hole in the valence band. Such type of doping is called p-type doping or acceptor doping, because the impurity is called acceptor impurity due to, for an obvious reason, it accepts an electron from the crystal. The semiconductor is called p-type semiconductor, and holes in the p-type semiconductor become majority carriers, whereas electrons in a p-type semiconductor are called minority carriers. So again, the concentration of majority and minority carriers is intrinsic concentration squared due to the mass action law. So if acceptor impurities make the whole concentration bigger by 1,000,000 times relative to the intrinsic concentration, then electron concentration will be smaller by 1,000,000 times. Okay. All right. So, and then there is, of course, another type of semiconductors, compensated semiconductors, which contain both donor and acceptor impurities. Such semiconductors are also used. Sometimes the same atom can act both as a donor and as an acceptor. That's a little bit funny, but okay. So let's say your semiconductor is gallium arsenide. Gallium is group 3, and arsenic is group 5. And you dope it with silicon. Now, silicon can replace either gallium atoms or arsenic atoms. If it replaces gallium, then a silicon atom becomes a donor. If it replaces an arsenic, then the silicon atom becomes an acceptor. So, all right. So okay, so I have already said these words, but let's repeat them. In N-type semiconductors are the ones which are doped with donor impurities, such as phosphorus and silicon. In N-type semiconductors, your electrons are majority charge carriers, your holes are minority charge carriers. In p-type semiconductors, the impurities are acceptor impurities, with majority carriers being holes and minority carriers being electrons. No matter what semiconductor type you have, the mass action law must hold, which says that the product of majority and minority concentrations is the intrinsic concentration squared. Now, we know how to express the intrinsic concentration. We know what the intrinsic concentration is. It is we have actually three different expressions for the intrinsic concentration. The first one is the whole concentration, but replace the Fermi energy with the intrinsic Fermi energy. The second one would be the electron concentration, Nc times exponential to the power minus Ec minus E Fermi intrinsic over kT. Getting from talking. So electron concentration. Then the second expression for an intrinsic concentration is the whole formula, Nv times exponential to the power Ev minus E Fermi intrinsic over kT. The third expression is the geometric average of the two, square root of Nc Nv times exponential to the power negative bandgap energy over 2 kT. Now I would like to relate the Fermi energy in a doped semiconductor to the concentration of its charge carriers. Let's start with electron concentration. N naught is Nc, effective density of states in the conduction band, times exponential to the power negative Ec minus E Fermi over kT. Now, in this exponential, let me add and subtract intrinsic Fermi energy. So Ec minus E Fermi intrinsic plus E Fermi intrinsic minus E Fermi. So this operation doesn't change anything. Notice that Nc times exponential to the power negative Ec minus E Fermi intrinsic over kT, so the first two terms right here, this gives me intrinsic concentration in the semiconductor. So I relate the electron concentration to intrinsic concentration as N naught is N intrinsic times exponential to the power E Fermi minus E Fermi intrinsic over kT. And by performing the same operation for whole concentration, so P naught is Nv exponential to the power Ev minus E Fermi over kT equals Nv exponential to the power Ev minus E Fermi intrinsic plus E Fermi intrinsic minus E Fermi over kT equals, and then this thing. P naught equals N intrinsic exponential to the power negative E Fermi minus E Fermi intrinsic over kT. So these two formulas relate the concentration of electrons and holes in a doped extrinsic semiconductor to the intrinsic semiconductor, intrinsic concentration. Both formulas still involve the Fermi energy. So both formulas, we still need to somehow figure out the Fermi energy. But I would like to make the following observation. If Fermi energy is higher than the intrinsic Fermi energy, then this exponential in the first expression for electrons becomes bigger than 1. So, and in the intrinsic concentration is multiplied by a number which is bigger than 1 to give the electron concentration, which is characteristic of the, which means that the semiconductor is of n-type. If Fermi energy is higher than the intrinsic Fermi energy, then the semiconductor is of n-type. And if Fermi energy is lower than the Fermi energy, then it is the whole concentration which will be bigger than the intrinsic concentration. The electron concentration will be smaller than intrinsic concentration. So in semiconductors of n-type, we have the following hierarchy of concentrations. Hole concentration is the smallest, electron concentration is the biggest, intrinsic concentration is in the middle, and n-type semiconductors. Whereas in p-type semiconductors, hole concentration is bigger than intrinsic concentration, and intrinsic concentration is bigger than the electron. And here is the last slide. Energy band diagrams. So energy band diagrams is a schematic way of showing the important energy levels in the semiconductor. And for now, the most important energy levels are the energies at the band edges, Ec, Ev, the Fermi energy, which may be in the upper half of the band gap or in the lower half of the band gap, depending on the type of the semiconductor, and the intrinsic Fermi energy. So the first diagram describes an n-type semiconductor. Fermi energy is closer to the conduction band edge, which means that electrons are the majority carriers and holes are minority carriers, n-type semiconductor. And the second diagram corresponds to the p-type semiconductors. Fermi energy is below the intrinsic Fermi energy. It is closer to the valence band edge. So in general, again, if the Fermi energy is closer to the valence band edge, EV, the semiconductor is of p-type, holes are majority carriers, electrons are minority carriers. If the Fermi energy is closer to the conduction band, electrons are majority, holes are minority carriers. What is on the x-axis of the energy band diagram? Just the spatial coordinate x. Just so imagine like a piece of semiconductor, and as you go in the x direction, let's say here you have the boundary and the x-axis is perpendicular to the boundary, and as you move along the x-axis, if the doping profile of the semiconductor doesn't change, your bands will have the same, the band energies will have the same values. So the horizontal axis in the energy band diagram, which is usually not shown, but nothing speaks against showing the x-axis. This is the normal spatial coordinate x. So with this, I would like to conclude this lecture. And thank you very much for your kind attention. Goodbye.